Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of Module 3. In this lecture today, we shall discuss other subsystems of the stereolithography apparatus, and those are galvanometer and recoating systems. As we have already seen this, the 3D systems SLA and 3D systems SLA based on Zephyr both uses galvanometer. So, it is the most important unit which is typically used in SLA and even today in the modern days wet photopolymer based 3D printers. This part we have already discussed, as we have already seen how a laser propagates and the different properties of a laser. Also, we have seen the curing process in detail, where we discussed about the single bead curing, multi bead curing and multi-layer curing as well. Now, today our focus will be on the galvanometer. So, the laser beam is basically positioned by using two small mirrors, one like you are seeing here, one mirror here shown, another may be there in another direction, and these mirrors are capable of deflecting the beam in two directions. Being a very low inertia of these mirrors, the scanning speed can be very high. Now, so let us discuss about the galvanometer. Typically in the market, a galvanometer looks something like this. As you can see here, there is one mirror, it is highly reflected, and another mirror here. The axes of these two mirrors are perpendicular to each other. Here you can see, if a laser light is coming from, for example, this end, it will get deflected on this mirror and it will go up and will again get deflected on this particular mirror, and hence it will get out like this. As you can see, each mirror, this is for example mirror 1, it is attached with a motor. This is motor 1. Similarly, this particular mirror, that is, say it is mirror 2, it is attached with a motor 2. As these mirrors rotates or oscillates, the motion of the laser beam will also given appropriately. If this mirror will rotate, you will get in perpendicular direction. Hence, you can utilize the 2D area by using such galvanometer systems. So, what basically happens? I will show you one prototype which I have made just to show how beam get deflected on this galvanometer system. So, here this is the prototype which we have made for you to further explain the galvanometer in the working condition. Here what you are seeing, this is the laser pointer which we are considering as a fixed laser beam on the right side. The laser beam is falling on this mirror, and then after reflecting from this mirror, it is going on the top mirror which is deflecting it back on the surface. Assume that this is the surface where your wet photopolymer is. Now, the deflection corresponding to this second mirror is making this beam to move in this direction on the bottom surface, and the deflection of the mirror 1 is moving this beam in this direction on the bottom plate. The appropriate motion of the two mirrors can appropriately define the motion of the laser beam spot on the bed, as you can see here. Right now, the laser beam spot is moving in a rectangular path. Of course, in the real life, the hands are replaced by the two motors corresponding to the mirror 1 and mirror 2, and the appropriate rotation of the same can move the laser beam appropriately. Another interesting thing can be observed here. A tiny motion of these mirrors is capable of moving or deflecting the laser beam with a very large distance on the bottom side. However, it is obvious that when the laser beam is projecting at an angle on the base plate, not perpendicularly, the shape of the laser beam will get disturbed. So as we have seen, let us try to put all these things on the paper. Here there is one motor. This is called as x-axis motor. This is motor 1 for example, or motor X, and this is motor corresponding to the y-axis. So as this mirror is attached with this motor shaft, when the motor oscillates, this mirror will also oscillate back and forth. Similarly, the shaft of this motor is also attached with the mirror, which is shown here in brown color, and as the motor oscillates, the laser beam can move back and forth along the y-axis. So as you can see, as the laser beam is striking at the center of this mirror, and for example, if the mirror is at 45 degree, it will deflect this mirror back to this particular mirror, which is shown here in brown color, and it will deflect it downward at the origin. So both the mirrors are at home position right now. Now what will happen if this brown color mirror moves to the new position, which is shown here in pink color? That means this, because of the motion of this angle, as it came like this here, it goes up like this, the beam will move from this point to this point. It is obvious. In a similar fashion, if this particular mirror is stationary, it is not moving, the brown one, but the blue one has moved. Now the old position is pink and the new position is shown here in blue mirror. So what will happen? Earlier the beam was going like this downward. Now due to the new position of the mirror, which is here, as it can be obtained by the rotation of this angle, the laser has moved to a new position here. So it has moved along this axis. Now let me consider the case when both the mirrors will rotate. So let us assume that this is your laser beam, which is shown in red color here. When it strikes with this pink mirror, the color of the ray is pink. And further, if it strikes with the green mirror, means the green position of the mirror, that means it will go downward. Hence the ray is shown here in pink plus green color. This is for your understanding. Now if this pink ray will strike with the brown color position of the Y mirror, then the ray will look like this. It is half in pink color and half in brown color. And it is obvious, it makes us to understand very easily that if the laser beam is falling down like this, and if this Y mirror is moving, hence obviously this laser beam spot will move from point A to point B. Now if, let me consider another case, the Y mirror is stationary and here the ray is coming, which is in red color, and if it is striking with the blue mirror, which is the new position of the mirror, X mirror basically, then if it is strike with the green position of the Y link, then this ray, which is a combination of blue and green color, will show the new position of the beam. It is obvious, as there is an angle between this, obviously the same angle will be incidented by this line OC3 here, as per the law of reflection. Now what will happen if the Y mirror also moves? If both the mirror moves, the position of the different beams are shown here. So this is very important to understand. Now this is the red color beam which is coming from the laser. If it is strike with the blue position of the Y mirror, the reflected ray is shown in blue color. If it is then strike with the brown color position, this is the beam which is a combination of blue and the brown. In a similar fashion, if it is strike with the pink color of the mirror, and then the laser beam is shown here in pink color, and after that if it is strike with the brown color mirror, then of course this particular beam which is shown here half pink half brown is the deflected beam from this mirror. Now in a similar fashion, if the laser beam is striking with the green position of the y-axis mirror, then in that case it will go like this. Hence the combination of pink and green is showing the ray corresponding to this particular condition. In a similar fashion, this particular ray is showing the combination of when the ray strike with the blue position of the X mirror and green position of the Y mirror. Here some of the dotted lines also you are able to see. These are nothing but I am drawing the vertical drop from these points. So for example, if the laser is striking here, it is going away, means it is making some angle, and this angle is the angle coming because of the reflection in the mirror. But if I draw the normal also, then it will fall like this. In a similar fashion, I am drawing this particular line which is coming because of the motion of brown mirror, because of the new position of the Y mirror. It is going to the position D, but if I draw a simple perpendicular, then it will be D dash. It will be perpendicular in a plane which is basically like this. So that is why it looks like this. So it is still a 90-degree angle in this particular plane. So try to visualize this plane. It is not a plane in this paper. It is tilted like this. So now our objective is to find out the relationship between the theta x and theta y. Theta x and theta y are the angle of the deflection of mirror corresponding to the x axis and mirror corresponding to the y axis. Our aim is to find out a relationship between theta x and theta y and the position of a point of the laser beam spot on the xy plane, that is x comma y. So for that, let us try to understand some of the geometry here, like angle O1 O2A is 90 degree. So this O1 O2A. So laser beam is striking here. This is the point O1. Then it is striking here because of the pink position of the mirror. This is the pink position of the mirror. It is going here, and then it is falling down like this here. So this angle is of course 90 degree. This is because both the mirrors are at 45 degree angle, and hence they are not deflecting, they are just putting the laser beam at the origin, that is 0, 0. Therefore, this angle will be obviously 90 degree. Why 90 degree? Because the incident angle and the reflected angle both are equal. So now let us see another angle, that is BAO2. Means this is B, this is A, and this is O2. This angle is also 90 degree. This is because this particular point is achieved when this particular mirror, y-axis mirror, has moved from green position to brown position. Hence the laser beam has moved simply in this direction to here, and hence as this angle was already 90 degree, it will remain like this. So angle BOA2 is 90 degree. Similarly, angle CC dash O3, C dash and O3, here this angle is 90 degree. Like I have already mentioned, if the ray is coming and it is getting deflected by the blue mirror, means the blue position of the X mirror, then instead of going like this, the laser beam will deflect it and go here like this. As now it is making some angle, it will again deflect it at an angle because of law of reflection. But if I draw a vertical line, just vertical line at this plane, hence definitely this will be at 90 degree because I am drawing a vertical line from here. So the angle C dash and A is 90 degree. Then angle D dash and O3 is also 90 degree. Here you need to visualize this particular plane. So what is happening, this particular plane which you are seeing here in the gray color, this is the particular plane on which I am considering it as 90 degree. So basically, if this angle is 90 degree, if I consider now this plane, angle D dash O3, this will also be 90 degree. The laser beam has deflected to point D, but I am talking about this particular C1 dash, I mean the C dash point only. It will move in a sphere like this, right? So this is the point I am talking about in this particular plane. Hence the angle D dash O3 is also 90 degree. So as they are following law of reflection, which states that when a ray of light, let me just draw it, if for example this is my plane, and if a ray of light is reflected from a smooth surface, so this is for example the light incidenting and this is the light reflected, then in that case the angle of reflection is equal to angle of incidence, means this angle, if it is theta, this will also be theta. And the incident ray, the reflected ray, so for example this is the incident ray and this is the reflected ray, and the normal which is drawn at this particular surface, okay, corresponding to this particular surface, this is the normal, they all will lie in the same plane. Based on this principle, one can deduce the following two expressions. Those are the angle O2, O1, O3. This is O2, this is O1, this is O3. This is nothing but the angle theta x, right? This is nothing but angle theta x, by which your x-axis mirror has rotated. So, this angle O2, O1, O3 will be equals to CO3 C dash, CO3 C dash, meaning to say this particular angle. So, this angle will be equals to this particular angle. And it is obvious also, as because this particular ray is drawn when it is falling at the center, meaning to say this particular ray is achieved when it is at home position. Hence, when this particular ray will also drop like this, we'll assume that there is a drop. I am drawing a dash line here. This particular angle will also be theta x. As this theta x will be 0, of course this angle will be 0, and hence your line will be nothing but vertical line like this. Also, this angle is equals to DO3 D dash. This is DO3 D dash, means this particular angle. This is also theta x. It is because of the rotation of y-axis mirror from green position to the brown position, the whole thing is moved. I mean, just assume that this whole ray is moved to this position. Hence, this angle will not change. So, D dash is nothing but the motion of the C dash when the y-axis mirror is moving from green position to brown position. Hence, all these angles are equals to theta x. Now, let us see what will be theta y. So, theta y is the angle O2BA. So, this is point O2, this is point B, and this is point A. Hence, this angle is theta y, and of course, it is nothing but the rotation of this mirror. If this angle is theta y, then of course, angle C dash, D dash and O3, this is O3, this particular angle will also be theta y, because they are nothing but, you can see, all are the parallel triangles, right? And again, like I said, CD and O3, this particular angle, CD, O3, this particular angle up to this point will be also theta y. So, all these angles are theta y, theta y, theta y. Hence, I can write this expression. Now, let me consider the distance between mirror 1 and mirror 2, that is represented by distance O1, O2. This particular distance between the two mirror is given by E. So, O1, O2 is equals to E. And if I am assuming that this first mirror, which is Y mirror here, and the distance basically O2A, or in other words O3C dash, these two distances, those are same basically, are equal to H. So, these distances are equals to H, means the height. So, if this is the wet photopolymer bed, this is the wet photopolymer bed, the height from this particular mirror to this wet photopolymer bed is given as H. So, now let me consider this right angle triangle, that is O2AB. In this right angle triangle, this distance which is from A to B is nothing but your coordinate y. So, if I am talking about this particular point which is represented by x comma y, of course, this distance CD which is equals to AB is nothing but y. Hence, I can write this distance y equals to, which is AB, equals to h into tan theta y. This is height, and this angle I have already mentioned that this particular angle is nothing but theta y. Hence, I can write y equals to h tan theta y. So, this is my equation 1. Now, my aim is to find out this coordinate x. So x is what? X is nothing but d dash plus d dash b. So I am writing it as bd dash plus d dash d. It is obvious that bd dash, this particular distance bd dash, is equals to the distance O to O3, because they both are parallel lines. Hence these two distances are also same. So O2 O3, if I'll consider the triangle, this particular triangle O1 O2 O3, this particular triangle, I can easily locate this, because in this I know this is at 90 degree and this angle is nothing but theta x. So if this is 90 degree and this is theta x, I can easily find out O2 O3, and if I know O2 O3, like I said, it will be nothing but equals to BD dash, like here, and hence it will be equals to E. E is nothing but this distance, like I already mentioned. E is nothing but the distance between the two mirrors, that is E. E tan theta x. So now our aim is to find out DD dash. So how can I get DD dash? So DD dash, if I look at this right angle triangle, this particular triangle, and it is right angle because I am considering this particular plane, right? We have already discussed that. So this angle is 90 degree. If this angle is 90 degree, then of course O3 D dash will be this perpendicular line. Hence I can write this base which is of this triangle. I am talking about triangle DO3 D dash. So in this I am talking about triangle D dash O3. So in this triangle, this length DD dash will be equals to, if I look at this particular length, O3 D dash tan theta x. So finally, now I need to find out only OD dash. Why theta x here? Because this angle is also theta x. Here it is, we have already discussed that this angle will be theta x, this angle will be theta x, and this angle will be also theta x. Hence now I can write further O3D dash, which is this length O3D dash, it will be equals to O2B. This is your O2 and this is your B, because they both are parallel lines, right? And parallel and equal lines. So this length and this length, they both are equal. So O2B. Now O2B is very easy to find out, because O2B is in this triangle and this we have already seen. O2B will be nothing but root over y square plus h square, as you are seeing here. And hence this expression is root over h square y square tan theta x. So finally now I can put both these values in this equation back, and I can obtain x equals to E tan x plus h square plus y square tan theta x. This I am calling it as equation number 2. So these are the coordinates of point D, and hence I can write the point D as E plus root over h square y square tan theta x, that is x coordinate of point D, and h tan theta y, that is your coordinate y of point D. Now let us solve a problem based on galvanometer. In a polymerization based liquid additive manufacturing process, a vat of liquid resin has been used. A laser beam is used to selectively scan the required area on the surface of liquid bed. The maximum build volume envelope is 500 by 500 by 550 mm cube. The length of the bed is 500, the width of the bed is 500, and the depth of the bed is 550 mm. Now what will be the distance of optical system from the surface of liquid bed? It is asked to assume that the distance between the x and y axis mirror is 100 mm, and the x and y mirrors can oscillate between plus minus 22.5 degree. Meaning to say, On one side, the galvanometer can go maximum up to 22.5 degree. So assume that if the galvanometer is mounted at the center, you need to go on one side 250 mm and on another side 250 mm. And it should happen, this 250 mm distance should be traveled when the galvanometer deflects by 22.5 mm. Sorry, the 22.5 degree. So assume that this is a typical galvanometer system where this is the x-axis mirror and this is the y-axis mirror. The distance between x and y-axis mirror, which is O1, O2, or defined as by E also, is given to you. It is 100 mm. What is asked? It is asked that the distance between this point here O2 and A should be what? So this distance usually we have seen also is represented by H. Now we have to design this galvanometer system or this machine in which we have to find out the critical value of this H or the minimum value of this H. Of course, maximum its value can be anything. Like if it is at infinity, you know that 0 angle has to be rotated to scan anything on the bed. If the value is very large, in other words, the theta will be very less. So this will be our limiting thing. It says that within the deflection of 22.5 degree on one side, laser beam should be able to move to point B, it should be able to move to point D, and it should be also able to move to point C. Let us first consider that the laser beam is able to reach to the point B. The coordinate of point B can be given as 0 in x direction and in y direction 250. From the equations we just derived in few slides back, you can utilize here, and y will be equals to h tan theta y. And this is the point where we want to reach in the beginning. So to reach this particular location, the value of h can be easily calculated as h equals to y divided by tan theta y, where y is 250 mm, it is divided by tan 22.5. I am putting here the maximum possible value of the theta. Hence the minimum value of h, which is coming to be, is equals to 448.149 mm. Of course, in this case x is 0, therefore I cannot calculate the value of h from this equation. But this equation says that to reach at this location, you need minimum this much height of the optical system from the liquid bed or the surface of the liquid bed. Now let us consider another point C. So if we are considering the point C, the coordinate of this point will be 250, 0. And in that case, of course, y is 0. So I am not using that equation, which we just used in the previous point. But the equation x equals to e plus root over h square plus y square bracket tan theta x will be utilized here. As y is 0, this will be of no use. And hence we can simplify this equation, and h will be equals to x divided by tan theta x minus e, where tan theta x, in this theta x is nothing but the deflection of the mirror, the x mirror, and I am going to put its maximum possible value. In that case, I am getting h equals to, after putting all the value of e is nothing but the distance O1, O2, that is given here as 100 mm. We will get h is equal to 348.149. So for this particular, to reach at this location, point C, you require the height of the optical mirror, meaning to say the distance between the optical mirror and the surface of the liquid bed should be minimum 348.49. But as the previous case says the minimum distance should be 448.149, that means that should be our consideration in the design. But now let us consider one more point, that is point here D. And if the beam is able to reach at this location also, that means it can reach then at anywhere in between the region lying in the square ABDC. So we are considering now the coordinate of this point D, and they are 250, 250 mm. Now in that case, let us use first x equals to e plus root over h square plus y square tan theta x, where y is 250 and e is 100. Then and also theta x is 22.5 and x is 250. By utilizing these numbers,
we can find out the value of h. The value of h by using this equation is coming to be 242.29, which is further less. That means still the solution for this question is h equals to 448.149, because that was the maximum value we got for h, and that should be the minimum value we should use in the while designing the machine tool. Now also let us consider the another coordinate, which is y, and y is equals to h tan theta y. Hence h is again coming to be equals to 448.149. So among all these calculations, the maximum value of h is coming to be 448.49, and that is the required value. Hence the minimum value of the distance between the optical system and the liquid bed should be h equals to 448.149. Of course, larger than that you can have any value. If it is like 500 mm, then of course your deflection angle will be less than 22.5. But if it is less than 448 mm, or precisely less than 448.149 mm, then definitely more deflection angle will be required, and yours may not be make your system with these parameters.
Now it can be also observed from our derivation so far that the x coordinate is function of theta x and theta y both. Hence if theta x is constant, then I can write it like this also. So as we have seen that theta x, so how we are writing the x coordinate? The x coordinate is written like this: x equals to e plus root over h square plus y square bracket t theta x, and y is equals to h t theta y. So if I put this expression of y here in this equation, then x will be equals to e plus root over h square plus h square t theta y square into t theta x. So here we can see the coordinate x, it is a function of theta y as well as theta x. Therefore you can see the motion of theta y will also affect the coordinate in the x direction. Now let us consider that if theta x is constant, I am assuming that this theta x is constant, so I am bringing it in this direction. Okay, so I am rewriting this equation like this. So x divided by tan theta x will be equals to e plus h square plus y square. Now if I take the square of both the sides after keeping the e on this side, then this will be the equation. And finally if I further solve it, the final equation will look like this. And of course here y is equals to h tan theta y. What you are seeing in the above equation, it shows that with constant change in theta y, if theta y is constant, the scanning pattern will be a hyperbola. Meaning to say, if there is a constant change in theta y and theta y is changing constantly, then what I will get in this direction, a hyperbola scan like this. Correct? I am not considering that it is not changing, right? Only this theta y is changing, and that too with a constant rate. Hence you will get nothing but a hyperbola like this. You can also write a program and check this. So simple program I am writing. So I am varying my theta x from minus 22.5 to plus 22.5 with a step over of 0.5, and similar way I am changing my theta y, varying it from minus 22.5 to 22.5 with a step over of 0.5. As a result, your y, the coordinate y coordinate, will be equals to h into tan theta y. We have already seen that it is nothing but y equals to h tan theta y, and your x coordinate will be equals to e plus root over h square plus y square into tan theta x. So I am storing all these values corresponding to x and y when I am scanning on each and every point, and you will see this is the result I am obtaining. Here you can see these edges, they are scanned like a hyperbola, right? If I just scan this particular lines, right, meaning to say there is a constant change in theta y, and hence you will achieve nothing but the hyperbola. Hence we have to be careful when we are going to scan on a boundary. We have to be careful because if you are moving only in y direction, there will be a change in theta y, and as there is a change in theta y, there will be a corresponding change in the x coordinate also, because x is a function of theta y. Hence, you have to accommodate that. So, let me just try to obtain that again in the reverse manner. So, for example, I want to move on a boundary. So, this is a boundary. I have loaded a boundary which is a text file and it corresponding to some coordinate point like x1, y1, x2, y2, x3, y3 and so on. So, these are some points corresponding to a boundary. Boundary may look anything like this. What my objective is, I want to obtain for each and every point what will be the position of theta x and theta y, so that I can give this input to my galvanometer and say that move the laser beam spot to this point, to this point, to this point, to this point, to this point. And what are these points? You have already obtained these points. We have already learned that how to obtain intersection between the plane and the STL file. These intersection will give you nothing but the points, and I am moving, for example, on these points only. So, this particular file you already have by slicing. So, my objective is now to find out theta x and theta y, so that I can move my galvanometer along these points. So, you can easily write a very simple code. So, I am loading this file here. It is having all these coordinates and I am observing its size, and if the file size is, for example, there are maybe 1000 points. So, this will be the size of the file, and I will run the loop for 1000 times, because for each xy point I want to obtain theta x and theta y. That is my objective. So, I can easily find out theta y will be nothing but, you know that y equals to h tan theta y, right? So, theta y will be equals to tan inverse y by h, of course. And in a similar fashion, if you know this, you can find out tan theta x will be equals to x divided by e plus root over h square plus y square, right? And y square here is nothing but the second column of this particular file. So, I can easily locate theta x as well. Now, if I am writing, this is my point B1 and B2, this is basically x1 and this is this particular vector is showing the x coordinates and this particular vector is showing the y coordinates. Now, let me just plot and show you something very interesting. I want to move from this point to 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 this point and then this point and then back to this point. So, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8 and 9 points here, again the repeating point. So, if you just see, the corresponding plot of the angles is shown here. This blue curve is showing the change in the theta x, while the black is showing the change in theta y. So, what you can do basically, this is my first point, right? I am starting from here. So, if I am going from this point 1 to 2, I am going from point 1 to 2. This is my point 1 and this is my point 2. And then I am going from 2 to 3. So, this is basically point 3. So, it is a change only in x direction. There is no change in y direction. As you see this black line, it is not changing, means there is no change in theta y, and it is of course because theta y equals to tan inverse y by h, right? And as there is no change in y, the theta y will remain always same. It is not changing, it is same, continuously same. Fine. As it is not changing, of course your theta x will change because there is a change in x from this point to this point, and hence your theta x, hence your x is changing like this. Now, when you are moving from point 3 to point 5, there is no change in x. So, ideally your line, this x line should be a straight line, but it is not coming as a straight line. Why so? Because when you are changing only theta y, as there is a change in theta y, hence you are moving from this point to this point, theta x is also having, if you noticed, theta x is also having e plus root over h square plus y square. So this is the tan theta x, and if you observe here, as there is a change in y, of course there is no change in x, but there is a change in y, hence your theta x will also change. That is why you have to, if you want to even move in a straight line in y direction, your theta x mirror should also change. Only change in theta y will not allow you to move in a straight line in y direction. Then again, if I am coming from point 5 to 7, there is no change in this theta y, because there is only change in x, and hence only theta x is changing. It is coming from this point to this point. There is no change in theta y. Again, I am moving from this point 7 to point 9. There is a change in black color from here to here. That is your change in the theta y. And as there is a change in theta y, there will be change in theta x as well. Hence, it is coming like this. It is not a straight line. It is not constant. It is changing. So, this is how a galvanometer works. So, as we have already seen now how this galvanometer works, you can now easily convert the xy coordinates which you required in terms of theta x and theta y of the mirror angles. Now, there are some disadvantages and advantages of this process. The major advantage of this process is the involvement of the low inertia. As the mirrors are very tiny and they can deflect with a very high speed, and hence the laser beam spot on the xy plane can move with a very high speed. You can achieve this laser speed up to 10 meter per second here. As there are tiny mirrors involved in this process, the noise is also not there at all. Because of that, also the life of the galvanometers are quite high. However, there are certain disadvantages also. One of the disadvantages, when the laser beam strikes on a mirror, some of the energy get absorbed also, not entire energy get reflected. Because of absorption of some energy, the life of the mirror reduces. Either we have to have a proper cooling arrangements in that, or the reflectivity should be very, very high. Other than that, there are two major issues, those I am going to discuss in detail, and those are the defocusing of the beam and laser beam spot distortion. We will discuss these topics in the upcoming lecture. Thank you very much.